mentioned, my name is Enda Nicol from Analog Devices. I'm the marketing manager for magnetic sensors. And I'd like to talk to you today about the world's first single-chip multi-turn position sensor. There are many single-turn sensors on the market today. They could be magnetic-based, for example, Hall, TMR, GMR, AMR. They could be inductive-based. They could be resolver-based. They could be optical encoders. But they all have a limitation of a measurement range of 360 degrees or one turn. The AD-MT4000 from Analog Devices has an absolute measurement range of 46 full turns, which is over 16,500 degrees. And it's accurate to 0.25 degrees typically. So this sensor is set to revolutionize actuation control. And the product, just that you're aware, has released to the market about 3 weeks ago. So we have a lot of intense sampling going on at this moment in time, particularly into the industrial automation space. So in the whole world of robotics and humanoids, it's allowing our customers to simplify the actuators by the ability to count the turns without any power, is allowing the customers to remove linear transducers or backup batteries in combination with single turn sensors in their systems. So it's quite revolutionary, and we're very happy to introduce this to the market at this time. Well, how does it work? At the very core, the technology behind this is called shape anisotropy, which comprises of two structures. One is a domain wall generator, as you can see here on the left, and from that you have a very narrow basically leg, which is extremely narrow. It's nanometer geometries here. So this structure is made of a magnetic material. So when you rotate a magnet in front of it, the arrows, as you can see there, they follow the direction of the magnet moving. The domain wall generator, as you can see, the magnetization moves with the magnet. It starts the magnet. However, the very narrow spiral track here, the magnetization can only work in one or both directions. And I'll talk about that in a little bit more detail. So the other thing I wanted to mention is we build this structure on what we call a GMR process. So we have a fixed layer, a pinned layer at the bottom, and we have a flotation layer on the top. And so when you change the direction of magnetization on the upper layer, basically what happens is you change the resistance of the structure. So that's something that we can pick up then with our sensor. We take this core technology and we build it into a spiral of 46 turns. On the left here, you have 23 turns. It starts in this domain wall generator is in the center, and we have 23 turns moving from the inside to the outside. On the first part, on the second part, we have 23 turns moving from the outside to the inside. So that's the core, if you like, of the technology, and I'll talk about it in a little bit more detail. As I mentioned, you have a domain wall generator and a very narrow structure. If I move a magnetic field in front of this structure, you can see that the magnetization in the domain wall generator is now parallel to the very narrow track, and the magnetization in the track is parallel. If I rotate the magnet, as you can see here, 90 degrees, a domain wall is starting to generate at the entrance to the very narrow magnetic track. If I move it 120 degrees, you can see that it's starting to enter into the magnetic track. And if I move a full 180 degrees, you can see that the domain wall has shifted across the track and it has changed the direction of magnetization. So what we do, I'm going to give an example here of a two-turn sensor, which uses this structure. Here's our domain wall generator in the center. These are the narrow tracks creating a two-turn spiral. The dark arrow in the center is the direction of the magnetic field. The broken arrow is the pinned layer direction of the GMR. And the other arrow there is the direction of rotation, clockwise, in this case, of the magnetic field. So we apply a voltage and ground across the spiral, as you can see here. We have 4 contact points in this spiral, numbered 1, 2, 3, and 4. The blue lines indicate a low resistance value, and the red lines indicate a high resistance value. So at the moment, if I decide to turn the magnet 90 degrees, nothing has happened in the spiral at this point. If I move it 180 degrees, as I explained earlier, a domain wall has moved from the domain wall generator to the first ground position there, and that leg of the resistance has gone from low to high. If I move the magnet another 90 degrees, the domain wall has now shifted to the 0, 1 degrees. We read back that position through our ASIC, and you can see here that at point 1, we have a shift in voltage as a result of that change in resistance. Remember, this is built on a GMR stack. When you change the direction of magnetizations, you change the resistance of that leg of the track. If I continue another 90 degrees, you can see now that I've moved the first domain to the VDD. The second domain wall has shifted from the domain wall generator to ground. Okay, if I go again, yeah, you can see now that the first domain wall is at 0, 2. Back here at the blue line, you can see I've got a shift in voltage at 0, 2. So now I know that the spiral has moved through that number of turns, and the second domain wall has moved. The process continues. So I keep rotating, I keep moving the initial domain wall, and further domain walls move into the spiral, basically filling the spiral as the magnet rotates, and so on. So if I reverse the direction of the magnet rotating, I simply reverse the process. The domain walls move back through the spiral and into the domain wall generator. So I get the reversed effect. So effectively, the multi-turn sensor can count in both directions, clockwise, counterclockwise. So I suppose what value has this got in an end application? One major application is linear drives, rotary to linear actuators, or linear drives. As you all know, you're all working in the motion control industry, that typically for a rotary linear actuator, you need a linear transducer or linear position sensor to provide position feedback of that block moving over and back. Our multi-turn sensor, simply positioned against a dipole magnet at the end of the shaft, can provide you that exact information. Remember, the angle, it's accurate to 0.25 degrees over a full range of 16,500 degrees of range. So you're getting the extreme resolution and precision. So you can eliminate a high-end linear transducer in your drive. The sensor has got the multi-turn spiral, but it also has an AMR angle sensor on chip to allow us to get to the 0.25 degrees of accuracy. So as I said at the start, what this is doing is allowing our customers to simplify the actuator design. By removing the linear transducer, you can shrink the size of the actuator, you can reduce the weight of it, and reduce your overall system costs as a result. Similar in the robotic space, the humanoid space, in the rotary actuators and the joints, again, you can eliminate the need for rehoming a robot arm, or a humanoid arm, or a humanoid finger, or humanoid knee on power up. Or if you do a battery swap in the case of a humanoid, you know on power on the exact position of all the joints, of all the actuators, and you can continue on as normal without having to rehome and recalibrate. There are also a range of other diverse applications we've stumbled across over the last while, including wire drawing coders. It simplifies them significantly. Any sorts of lifts or hoists, winches, cranes, and so on and so forth. So the list is endless. We're also in medical equipment, XY tables and medical equipment. Even like a dentist chair is one application that we're involved with. So there's just a diversity of applications. If you move into the automotive world, the sensor can be used in a seatbelt system, so that when you get into your car, you put on your seatbelt before you put your key in the ignition, right? So what the car will then have recorded, or the sensor will have recorded, the number of turns of the spool. So when you key on an ignition, the car safety system will know exactly the classification of the occupant in the car by the extension of the seatbelt and how close they are to the airbag. And that determines the airbag deployment strategy in the vehicle. A new emerging market coming in a few years from now is steer-by-wire. Another application, you're removing the mechanical coupling between the steering wheel and the road wheel actuator. So you cannot rely on your steering angle sensor or your torque angle sensor anymore. So with that, then you need an absolute position sensor down at the rack. And as I explained earlier, you would typically need a linear position sensor down there, or you'd need to have gearing with your motor with single turn sensors to give you the absolute position. The ADMT 4000 can obviously eliminate all of those mechanics, simplify your system, and provide the true power on multi-turn position when you key on the car. So you can know your steering angle on key on. The product itself as I mentioned, released 3 weeks ago. It comprises 3 die in the package. It has the GMR spiral. And on the GMR spiral, we have also got a quadrant sensor. So we do a very simple quadrant sensor, and we have an AMR angle sensor. As you may know, AMR has a limitation of a measurement range of 180 degrees. So we take the multi-turn information, we take the quadrant information, we merge it with the angle information, we mux all that in, we do signal processing, we do mechanical calibration, we do harmonic calibration on chip, we have a temp sensor, and we provide an output through SPI. The automotive version of this will also have a set interface when it releases in 2025. Okay, so in a 24 lead TSAP, one thing you need to be conscious of designing the product in is the magnetic window. The magnetic window needs to be between 16 and 31 millitesla. If you go below 16 millitesla, you can potentially not have enough magnetic energy to move the domains out of the domain wall generator through the spiral. So that's the sweet spot. That's the point where you have enough energy to do it. Similarly, if you put too strong a field in front of the sensor, you're going to saturate the spiral and you're going to reset the sensor. Basically, you're going to fill the spiral with domain walls and reset the sensor. So it's important that the application is designed with a magnetic field of between 60 and 31 millitesla. Operating temperature minus 40 to 125. It's in a 24 lead TSAP. So one of the questions we get a lot is about stray fields. Okay, so if there's a stray field in the environment, will it corrupt the sensor? It's like any other magnetic sensor in the world. Naturally, an interfering field can impact it. So what ADI have done is we've created a reference design magnet with an inbuilt shield. Now this was designed for a very harsh automotive environment. We attach the shield to the magnet assembly. As you can see, the magnet is initially overmolded, and then the magnetic shield is assembled to the magnet. So what this provides is robustness up to plus or minus 5 millitesla in a harsh environment, in a harsh automotive environment. This is overkill for a lot of industrial applications because you don't have that same tough environment. So the magnet can generally be typically made much smaller and more compact than you can see here. And finally, how do you reset the sensor? So we would recommend that when the sensor basically is assembled into your system, there may be some corruption during transportation or during assembly. So what we recommend is the sensor be reset after it's integrated into the system. There are 2 ways to do that. You can reset by overturning. So simply rotate the sensor 46 times or beyond, 400 times. It doesn't matter. It'll stay at 46 turns, the maximum turn count. And then once you start counting backwards, 45, 44, 43, you'll operate as normal. The second way you can do that is apply a very strong magnetic field over 55 millitesla. That can be done with an external magnet. It can be done by bringing your system magnet that's already there closer to the sensor to make a higher field, and that'll reset the part as long as it's over 55 millitesla. Or finally, on the PCB, we can put a coil or give you a design for a coil which can be put on the PCB and energized externally with a very short pulse of current to reset the part as well. So they're the typical ways the product can be reset.